put this on the record for people. All right. So definitely two triangles. C1, we'd like to pair with little c1. So you get sine of 25 over 28 equals sine of c1 over 34. And then c1 is equal to 34 sine 25 over 28, right? Sine inverse of that. Sorry. So make sure your calculator's in degree mode. And then like we talked about yesterday, briefly at least, I don't know, you want to store this value when you're done, okay? I want to make sure you're doing this. So 34 sine of 25 divided by 28. And I'm going to store that value in alpha c in my calculator. Did you get 30.9? At any stage in the process here, if you have an answer that differs by a decimal place, then you need to do some soul searching, right? Like, what did you do wrong? All 6 answers I'm about to put up here, you should have exactly the same way. 3 sig figs and all 3 digits should be exactly the same 3 digits that I had. Never ever use a rounded value, so that's why I'm storing this value in C on my calculator. Did you see me do that? Okay. Store in C. All right. As soon as we have angle C1, I guess we're calling it, C1, we can find A1, right? Capital A1 is 180 minus 25 minus C1, right? So A1 is approximately, wait for it, 180 minus 25 minus alpha C. That's what I stored this value in, okay? 124 point something, so it's 124 to 3 sig figs, 124. All right, we are 2/6 of the way done. You like that? Now we need little a1, and now we have big A1. We can set up that relationship. We have sine 25 over 28 equals sine of A1 over little a1, so that A1 is equal to 28 sine A1 over sine 25. So A1 is approximately equal to, we're about to have it, it's 28 sine of the thing we just typed in. Again, don't type in 124 divided by sine 25 gives us 54.8. And again, let's make sure that all 3 of these answers are exactly what you have. Okay? So far, so good? We've just solved the first triangle. Noah? Yeah, maybe we should have. You're right. I mean, the degree mark makes that maybe clear, but you're right. Yeah, I mean, that would be good style. In fact, actually, really the best style would be to say the measure m of angle, right? If you're like a geometry teacher, then you might like make a really big deal about all that. Okay, great. I think we're ready for the second triangle. Now, I said at the very end of the class yesterday, I said the ticket to getting the second triangle is recognizing a relationship that exists between C1 and C2 in this picture. And you remember what I said? Remember what we determined that was? We used some geometric argument, a little proof. It's had involved an isosceles triangle. They're what? They're supplementary. So you need to recognize that in order to make this jump across the line in the middle of the PowerPoint, you need to recognize that C2 is supplementary to C1. So C1 is approximately, we're about to say it, it's 180 minus alpha C, there it is, 149 approximately, right? And actually, I'm going to store that in, how about C, okay? All right, I'm going to store that. I'm going to overwrite C with this new value. That's my new C. So excuse me, C2. C2 is approximately 149, but I've got the full value in my calculator. We are 4/6 of the way done, and now we're just going to repeat the exact same steps that we did over here. right? A2 we can get next. That's 180 minus 25 minus C2. So A2 is approximately 180 minus 25 minus 5.86. Degrees. Okay. And we're 5/6 of the way done. We just need A2. Yeah, so.
I was just wondering, like, when you round 3 to 6, because you use some of them, like, afterwards,
Yeah.
do you use the rounded 3
No,
to
no,
6
you never,
version?
there's never a time in this class where I will say, oh, you should use the rounded value in the calculation. Make sure every time, in every problem, this entire year and in the rest of your life, you always use the full value in the calculator, okay? Don't round, only round when you're reporting an answer, okay? So A2 has gotten exactly how A1 was gotten, sine of 25, we can use the same relationship over 28, is equal to sine A2 over A2. So that A2 is equal to 28 sine A2 over sine 25. All right, so, and actually, where did I do that one? Boom. How you like them apples? There we go. 6.78. All right, am I getting an amen on that? Do you guys agree? 28 sine of the thing we just got divided by sine of 25. All right, there it is. Those are all 6 answers. Again, let me just emphasize, like, I'm taking a point off. If that's like 5.87, sorry, like that's not right. Like you didn't do it right, all right? Something you need to be careful. And part of what we're assessing in doing this, part of what we're assessing is your ability to like use the calculator properly, right? You do need to know how to store. It's not like just a trick. It's like a required skill, right? Storing values on the calculator using the stored value is like a required skill. All right, hey guys. Thank you for being quiet. Emily, go ahead.
In the law of sines, does it matter if the sine of the angle is on the top or the bottom?
It doesn't matter. Yeah, we got Emily's law of sines, which goes A over sine A equals B over sine B, which equals C over sine C. Perfectly good. And actually, I've seen it rendered on formula sheets that way too, and stuff in official places. So, wonderful, yeah. Do whatever you like. Okay, let's go over the quiz. I have one more comment about the warm-up here too. Why is it that this is the first triangle you solve? We should have mentioned this. The fact that this happens first is a kind of a consequence of what happens here on your calculator, right? You want to say more about that, Maddie?
Because the sine value, or because
Sine inverse.
the inverse sine, that gives you the quadrant 1 value.
Yeah, it happens to give you the quadrant 1 value on your calculator.
Is it 2 or 4? I was supposed to.
Sine inverse?
Yeah, the other two, C2.
C2 is in quadrant 2.
Yeah.
Yeah, it terminates in quadrant 2. Yeah. So is everyone clear on that discussion? The reason your calculator spits this answer back is like, for a reason we've actually kind of touched on a little bit before. Sine inverse on your calculator always returns an acute angle. Sine inverse on your calculator never returns an obtuse angle, even though both 30.9 and 149 both have a sine of this, right? Does that make sense? The thing inside here, this ratio, both angles have the same sign. An angle and its supplement always have the same sign, don't they? Because they have the same height off the x-axis, don't they? The same sign. Because their y-coordinate is the same. We just talked about the definition. It's y over r. So the y-coordinate of an angle and the y-coordinate of its supplement, same thing, right? So that's why both these angles could come out. They both have the same sine value. Sine of, try it on your calculator. Sine of 30.9. Sine of 149. You'll get the same thing. Okay? So that's kind of a good thing to keep in mind, I think. Okay, so hopefully that suffices as far as like conversation around the homework. I don't know if there were other issues. We want to talk about the law of cosines with the remaining time. It's not a huge chore, but I think we're ready to do it here. All right, we framed this nicely yesterday, didn't we? Yesterday we started kind of giving you an overview. Thanks, guys. We gave you an overview of where we were and also where we're going, and this is now, we're here. We said we'll save for tomorrow these two cases, SSS and SAS, both of which we'll solve with the law of cosines. And I used that wording yesterday. I said we'll save it for tomorrow, we're doing the law of cosines. So here we are. Today is tomorrow. You with me? All right, everyone's good. I'll save it for now. All right, we'll talk. All right, so why can't SSS or SAS be attacked using law of sines? Well, if someone gives you all three sides and no angles, that's a problem. For law of sines, that's a problem because law of sines requires you to have angle side pairs in order to make any headway. Why is SAS that? Now I have an angle. Why is SAS, that is two sides in the included angle? Why is that a problem for law of sines? Well, you need an angle and the opposite side, and there you don't have it. So again, both of these are like an issue. The law of cosines is up here in this box right before you without proof. You can maybe play around and see if you can try to prove it. It's a little maybe more challenging to prove than the law of sines, but I believe in you. It's a little tricky looking, yeah. It's a little complicated, so read. And then before we leave this slide, we're going to start doing, I just have two problems for us to try today. But before we try those problems, they're pretty straightforward in the application. You just plug stuff in and solve for the thing you don't know. But we should make one observation. What happens if A is 90 degrees? Can you tell me? Just think about the question I just asked and have an epiphany. All right, so cosine of 90 is 0, and then just blah, blah, blah. What happens? If A happens, capital A, happens to be a 90-degree angle,
Then A is a hypotenuse.
cosine of 90 is 0, and this whole last term goes away, and what do you have? The Pythagorean Theorem. Why? Wait. Oh, because if A, the side opposite little a, happens to be 90 degrees, then yeah, this is just a more general version of Pythagorean Theorem. If A happens to be 90, you get the Pythagorean Theorem. Yeah, mine. Yeah, right? So this is you can just use this from now on instead of the Pythagorean Theorem. Well, I don't know. But yeah. I don't know if Pythagoras, I don't know. I don't think he deserves any credit for, actually he probably doesn't deserve any credit for the Pythagorean Theorem either. It's probably one of his minions or something. I will say one other thing too. I should have maybe put all three laws of cosines up here, right? Because there are, for any triangle that has sides labeled ABC, there are 3 laws of cosine formulas that you could set up. Here's one. We also have,
Would you have
thanks
A
guys.
minus B?
Thanks for being respectful. We also have B squared equals A squared plus C squared minus 2AC cosine B. We also have C squared equals, can you fill in the blanks, right?
Yeah.
So I didn't write those just to save time, but you understand that A can play the role of any one of the 3 sides, regardless of what the names of the sides happen to be in a problem, okay? So I didn't write the other 2 versions because they're identical with just the letters switched. Okay. With that in mind, let's start by solving, which case is this? Which case is this? This is side, angle, side. I'm giving you 2 sides and the included angle. Again, we should stop and appreciate the fact that law of sines doesn't help us here, right? Useless. So maybe the law of cosines will help us. Which version?
But once you get one, can you use the law?
Well, let's think about that. We'll have that conversation in a second here. I think that's an important question. Okay. Which version of the formula do you want to write down? I don't know. Like I said, there are 3 different versions of the formula we could write down. A squared equals whatever, B squared equals stuff, or C squared equals stuff. Yeah, maybe C squared equals stuff, because the angle we know at the end of that formula, C squared equals stuff, is going to be a cosine C. And we have angle C. So maybe that's going to be a good way to go here. So that is, I'm writing down C squared equals A squared plus B squared minus 2AB cosine C is the law of cosines. Okay? So C is equal to the square root of some stuff. A is 11 squared plus 9 squared. So yeah, bust out the calculator. 11, 9, cosine 100. Make sure you're in degree mode. And in a second, we'll write down the approximate value of c. It's going to be very exciting. Okay, here it comes. So you beat me to it. Oh, you're so fast. 11 squared plus 9 squared minus 2 times 11. All right. How you doing? Did you get 15.4 like I just did? Just verify out there. Okay, we are a third of the way done. We're doing great. We already have two sides. Now we have the third side. We already have one angle. We need two more angles. Okay, so now we need to think hard about how to get another angle here. Which angle do we want? I don't know. How about angle A or something? Okay. So, and actually, I don't mind. Maybe someone out there should try the law of sines. It's pretty quick, and see if you can get angle A. But I do want to. Can you hear me out for just a second? I do want to caution you about using the law of sines. We have to be very careful. Now, I happen to know verifiably that angle A is not obtuse. Do you agree?
Yes.
Yeah, because C is. All right, so I think we're good. And I think it would be safe to use the law of sines. But be careful, because if it happened to be true that it's possible that A could be obtuse, like say this first angle is like angle C happened to be 50 degrees. Completely possible. We can change the problem. Then is it possible that A could be obtuse? And then we have to be really careful, because the law of sines, if we do the law of sines, you know that it will only give you an acute angle when you do the inverse sine. So do you see the caution I have to lay before you about using the law of sines? Here I think it'll be safe and you'll be fine. But if if you're going for angle A and it happens to be obtuse and you don't know it, you're gonna be fooled when you do sine inverse on your calculator into thinking that it's an acute angle. So you just have to be really careful. I'm going to just demonstrate before you the technique that always works, and that's to use the law of cosines again. But if you know what you're doing, I do give you permission to use the law of sines. Okay? If you're careful and you know what you're doing, okay? All right. So how do we get angle A using the law of cosines? It's worth, even if you were about to do the law of sines, it's worth thinking about how you could use the law of cosines to get it. I'm going to write down the A version of the formula, right? A squared, this is the one that was up there. There it is. And notice that we know everything in that except for angle A, don't we know? We know little a, little b, and little c now. So I think we're ready to go here. Angle A is equal to cosine inverse of A squared minus B squared minus C squared all over negative BC. If you solve that for A, right? Capital A. Is that okay? Little inverse operations there, you get that. Okay. And then we just need to type that in. Here we go. Cosine inverse of, what's B? A is 11? Okay, so 11 squared minus 9 squared. Again, don't use a rounded value. Minus second answer squared all over negative 2 times 11 times second answer. What was that? So you see how I typed that in? What do you think of that? All right, so let's see if did I type it in right? Did you get 54.5 also? This is angle A, which is 54, we just discovered, is 54.5 degrees.
So we know the other.
And angle, what are we looking for? Angle B, that's what it's called. Angle B is 180 minus 100 minus A. So B is approximately. By the way, did anyone use law of sines out there, and did you get 54.5 also? Someone.
Why is this better for the obtuse function? Because cosine?
Yeah. Here, absolutely. I'm just demonstrating in the case where you don't know. You're right. Here, law of sines. If you're careful and you understand that law of sines is fine.
In this case, even in the case it's not this where you know it's obtuse, inverse cosine will also just return the acute angle.
No.
No.
Yeah, that's why actually we like inverse cosine. Inverse cosine has a different value in the first and second quadrant. So, because it's negative. So actually you're fine with inverse cosine. Yeah, that's like a nuanced argument, but I'm glad it came up. All right. So, all right, and then we didn't do this yet. Let me finish. 180 minus 100. You guys are already done, but here I got to catch up. 25.5 is that what you got? Did something go wrong out there? For this?
Yeah.
You were supposed to tell me. All right. Where did I go wrong here? 11? Oh, that's A. Here, I need to go back and type something else in here. All right, is this 15.4? Okay. And then, yeah, I think I typed in wrong. There it is, 9 is what that should have been, right? 44.8, is that what you said?
Yeah.
All right, you're supposed to catch me.
I just assume you're right.
You were just assuming I was right.
But the law of sines.
I'm not confident in myself anymore. Wait, what?
Yeah.
Does that mean if you use inverse sine or cosine and you do something better than 180 degrees? I mean, sorry, if you do a ratio that's negative, right? Will it return quadratic form?
If you do inverse cosine of a negative number,
Inverse sine of a negative number.
quadrant form.
Then if you do inverse
Of a negative number, yeah.
So if you do positive, cosine, sine, or tangent, it will always be quadratic.
Right. All right, next slide. All right, you're going to have to take this one home as a little souvenir, but I want you to try it right now. At least get started. At least start the thinking process behind this one, right? Can you guys stop talking for a second? Again, you need to be real careful about which approach you're going to take. Now, first of all, you know you need to use law of cosines. Which version do you want to use? Any of them work, right? If you're using a squared equals whatever, you're going to first be solving for angle A, which is fine. If you start with one of the other versions, you'll be solving for one of the other angles. Also fine. And then again, here you don't know which angles, maybe none of them are, maybe they're all acute, right? You don't know, but you don't know. So maybe one of them's just like a little bit obtuse, who knows?
Or we can have to
You
memorize.
just need to be really careful.
Or we're gonna have to memorize.
Yeah, there are no formulas on any tests. So. Okay, so I mean, with that caution, you can do this just like you did the second half of the last problem, right? Big A is equal to cosine inverse of little a squared minus little b squared minus c squared over negative 2bc cosine. Oops. All right. Well,
Okay, sorry, one last question.
I guess we're done.
If you have a negative number and you put it into inverse tangent, would it give you the second or the
Fourth quadrant.